Hello everyone, I'm Vincenzo, or Steam Ralph. We're here to talk about return-oriented programming and specifically how to create return-oriented programming payloads in an automated way. So what we're going to show you today is first, let's call it a real-life scenario where return-oriented programming payload is really useful. Specifically, we will talk about the pawn-to-own iPhone exploit that I and Ralph wrote for this year's contest. Then Tim will explain our algorithm for finding gadgets, and Ralph will talk about how to chain gadgets together to actually have a meaningful payload. And finally, we will show you a demo with of the compiler and of the pawn-to-own exploit. And finally, we will discuss with you further work in this direction. So I'm gonna make a claim here. My claim is that the exploitation of memory corruption bugs when non-executable pages are in place is not something that you really enjoy doing. Unless you can use return-oriented programming, because I don't know how familiar are you with writing exploit, but in the past, in the old good days, what happened was, okay, you have some data controlled by the attacker, you just point the instruction pointer to the data, and there you have your payload, so you can just execute the payload without any problems at all. When non-executable pages, here we are at Microsoft, so when DAP is in place, you cannot do anything like that, clearly, because you cannot execute the pages, so you cannot just put some shellcode in some pages on the heap or on the stack or whatever. So there are some scenarios in which actually return-oriented programming is way more interesting because it serves a double purpose. I'm going to explain why it serves a double purpose later. But basically, as I said before, what we did was to play this contest, which is held at Kansas West in Vancouver. And the goal of the contest was to have a working exploit against a non-jailbreaking phone. What our exploit was capable of doing was basically to exfiltrate the SMS database to a remote server by visiting a malicious page through mobile Safari. So to boost the Cyber Pompeii thing and to actually show off the fact that I know Latin, I'm going to start with Seneca quote. Seneca a while ago said, "Ignis aurum probat, miseria fortes virus," which in English, if you're not familiar with Latin, basically translates to fire tests gold as adversities challenge for strong man. So in my opinion, the entire exploitation game, so defense and attack, and well, defense and offense, is pretty much, well, this Seneca quote really applies to this game. Because since we have no way to prove that a piece of code is bug-free, what the defensive side does is to raise the bar so that only an handful number of really skilled attackers are able to actually write functional exploit. So when we were playing with the iPhone, there were two actually interesting challenges that we had to face, and those two are particularly interesting for our talk, and they are particularly important to understand why return-oriented programming is really useful. So the first thing is code signing. I'm not sure how many of you are familiar with code signing. So basically, code signing is some sort of strong DAP. And by strong DAP, I mean usually when you are writing an exploit for Windows, OS X, Linux, whatever, what you try to do to disable the non-executable bit on pages or DAP is to using a return-oriented programming stub. What you try to do is to allocate a page with a writable permission on the page, put on this page your payload, then change the permission on the page so that it becomes executable, and you point the instruction pointer there. So you can actually execute your non-return-oriented programming payload. Or when you have permanent DAP, you do have permanent DAP in some processes on Windows 7. There are some other tricks that Brett Moore, a researcher from a company called InsomniaSect, explained. I'm not going to go into many details about that, but there are ways. So there are ways to either disable DAP or break out of DAP. With code signing, you cannot do nothing like that for two reasons. So code signing is really simple. There are two rules. The first rule is that if a page was ever marked as readable, it can be marked as executable. What this means is that you cannot just put your shellcode somewhere, change the permission on the page, and jump to the shellcode, because the application will crash. The other rule is that a page cannot be executable unless the page is signed. Unless the page is signed, which means that you cannot just allocate a new page with executable permission and just execute something out of it. So the bottom line is that in order to defeat code signing, you have to create a complete return-oriented programming payload and not just a small stub that will allow you to break out of DAP. And the other interesting feature that iPhone OS has is sandboxing. So I'm fairly sure all of you guys know what a sandbox is. In short, a sandbox allows you to make sure that an application can't do specific tasks. Like it can be forking processes, reading files, writing files, opening sockets, or whatever. The reason why sandboxing is interesting for return-oriented programming is that usually, in order to break out of a sandbox, what you do is to chain together two exploits. So let's say you have a remote for the browser, and after that, you have a local on the operating system. This local allows you to break out of the sandbox, and then you're free. But the problem is that in situation where code signing or similar countermeasures are in place, the only way you can chain together these two exploits is by using return-oriented programming. So I guess the lesson here is that you actually sometimes are forced to create some really, really complex and long return-oriented programming payloads. So you better not do this by hand. And the last mitigation, which is really interesting and luckily for us is not implemented in iPhone OS, is other space layout randomization. So, well, other space layout randomization does something really powerful and pretty simple. Just make sure that all the libraries, heap, stack, and so forth are not at a predictable location, so that you cannot just rely on the base address of a DLL or the stack or the heap. And with return-oriented programming, this is actually a problem because you need to know the base address of some library because gadgets are going to be there. Luckily, we didn't have to actually break out of the sandbox because there was a glitch in the sandbox policy of mobile Safari, and we didn't have to face other space layout randomization. So probably I and Raf are not that strong man. But so I'm not sure how many of you actually know how a return-oriented programming payload should work. So I'm going to try to do a ROP 101. So the main thing that you need to have with a return-oriented programming payload is to make sure that the stack pointer points to some data controlled by the attacker. So so basically your payload is going to be a crafted stack. on this crafted stack, you're going to have the address of some gadgets and some data that is needed for those gadgets in order to like work and do their job for your payload. So imagine, imagine that each gadget ends with a return instruction. You know that the return instruction what basically does is to pop the instruction pointer from the stack and jump there. So what this means is that since our payload is actually kind of impersonating the stack, when the return instruction is executed here, it will pop the instruction pointer from our from our payload, and it will go on for any number of gadgets that we need to execute, as long as we make sure that the stack pointer is not modified. So that's basically return-oriented programming 101. So the way you usually go about creating a return-oriented programming payload is, first you need to find gadgets. For instance, on iPhone, given that there's no address space layout anonymization, you can use the entire address space. So all the libraries, the main binary, and whatnot. Sometimes, like on Windows, it's kind of different. Some DLL are not randomized, depending on the application and so forth. So, well, anyway, the first thing that you need to do is to find the gadgets. Usually, well, until now, a lot of people did this by hand. Pablo Sole from Immunity created a tool to do this in an automated way. Dino Daizovi did something similar as well for x86. We're going to show here methodology, well, an algorithm that is capable of doing this in a platform-independent way. So the next step is to chain the gadgets together, right? So to create that crafted stack I was mentioning in the previous slide. And once again, this is usually a step that in the past was done by hand, and it's really, really annoying. And instead, Ralph will show you how to do this with a compiler and with the help of a solver. What basically this compiler needs as an input is some sort of, well, an assembly-like language that specify what your payload is supposed to do, and it will give you as an output the chained sequence of gadgets. And finally, well, you need to test your payload on your target. This sounds like trivial, but for instance on the iPhone it's not. And we will just, well, later we will show you a demo of the working exploit for Pwn2Own, so probably we'll just go really quickly through the testing part. So now Tim is going to explain you how the gadget finding algorithm work.
Yeah, thanks, and a warm welcome from me to everybody here in the room as well. So what we're going to cover now is actually the gadget finding process. And first of all, we're going to define the goal of what the gadget finding process in our specific area of work here wants to actually achieve. Then we're going to motivate the whole thing, why we do this in a way that we look at it platform independently. I don't want to go into all the details today because there's tomorrow going to be a talk where we're going to see all the details while architecture independent gadget cert is really interesting. But I'm going to motivate the part for ARM here, and you're going to see that our approach here is a lot different to the ones that you just normally see with return-oriented programming. Then we're going to quickly cover the strategy that we use in the algorithms here specifically. Then we're going to cover the algorithms which we use for finding the gadgets, and then I'm going to go quickly over the results of the gadget finding process so that you know what you can do with this algorithm set that I presented to you here without like the SMT solver part. Okay. Our goal definition is that we want to have an algorithm which is capable of locating gadgets regardless of the fact or which architecture we have, and we want to have that without the major side effects. Because side effects are one of the major problems that we face with all return-oriented programming approaches. As all instructions, as you normally know from x86 assembly language or something like that, have side effects like flags or undefined behavior or something like that, we actually have to take very special care if we want to chain code that should not be chained in this way we want to chain it. Okay, so what's the motivation? Basically, all of the phones that we have in the market today are based on ARM-powered processors. And also your new Windows Mobile 7 phone series, which you released on Monday, is also based on ARM processors and all the devices that you have. MIPS is pushing in the market as well, but they haven't released any phones as to my knowledge quite yet. But the ARM processor is one of the most sold or most licensed processors that we see today. So it's one of the primary targets, not only for the phone market, as you see here, but also for all the other devices which in the future will get CPUs and processors. So in Germany, what we have currently is a very high hype for those automated vacuum cleaning machines that go around and clean your room when you're not there and stuff. And also you can think of a refrigerator that you have a barcode scanner in and it checks for your milk getting sour on a certain day and connects to the internet so that the dealer brings in new milk on the next day so that you're never starved of milk, and solving the too much milk problem in something like that. Okay, yeah, basically we see that we won't have any Intel iCore 7 machines in any of those devices because your vacuum cleaner would run out of power immediately after leaving the docking station. So it doesn't make any sense. Okay, so what's the strategy behind our work here? What we do is we only use code which is already present in the binary. That's generally, with all return-oriented programming, that's the approach we're going to use. And in contrast to a whole lot of the other approaches that use return-oriented programming, what we do not want to do is a single instruction return-like approach. Because in the architectures we also want to look at that are strictly aligned, in contrast to a variable length instruction set that you see in x86, we have the problem that we cannot go for unintended code sequences as easily as you could do that on x86. The return instruction on x86 only 1 byte, but with all return instructions that you have in ARM, they are always 32 bytes, and the same thing for all other RISC architectures that you can think of. So what we actually look at is an approach where you chain multiple instructions to form a gadget directly and not to look at single instruction return-like sequences and then form a gadget out of many of those. Okay. To be able to be platform independent, we need some kind of way to abstract our native assembly languages into something that we can work on and have the algorithm perform on, which is not dependent on the underlying architecture. And what we use here is the at Cynamics developed reverse engineering intermediate language. And I'm going to briefly cover what it's all about in the next slide, so don't worry if you never heard of it before. Also, as in many of the RISC instruction sets, and also in x86, you not only have return instructions which you can use to alter code flow. We don't only use return instructions in general, but we define something what we call the free branch instruction, so that we have multiple opportunities to actually and chain gadgets with, so that you are able to use leave kind of functions where no stack pointer change is happening and stuff like that, so that we are not limited to any of the only return functions. Also, we use a first find all, then filter useful ones approach, which means that we scan the complete library, collect all the possible gadgets from it, and then later in the chaining process select only the ones we need. Also, we need to keep keep an eye on side effects and minimize them, because if we won't do that, then the SMT solver we're going to later show here will have a problem because it's going to take forever. Okay. As I mentioned earlier, we use the reverse engineering intermediate language, and you might want to know what it's all about. The reverse engineering intermediate language is nothing else but a small RISC instruction set of only 17 instructions, which perform like arithmetic, control flow, and other things that you need for, like, example, unknown instruction when you don't have a translator for that specific native instruction, or it sets something to undefined if your instruction set has something like that. So that's one of those other functionalities. All the instructions that you have in RILE are completely side effect free. And that's one important thing that you have to keep in mind. with most of the instructions that you have in native instruction sets, there are always side effects that might or might not happen while executing this native instruction. Think about like an add instruction on the x86 assembly. It is always able to set flags depending on the outcome of the operation of the instruction. With the RILE instruction set, those side effects do not happen because only the register which is in the instruction as target will be changed and nothing else, so that you know exactly what will happen. Therefore, every instruction that you translate to RILE will result in multiple RILE instructions, at least like for almost all of them. Okay, then RILE has an interpreter where you can actually execute RILE code in with virtually unlimited memory and temporary registers, depending on your machine, of course. And it's implemented as a register machine to closely resemble the architectures that we want to take a look at, like x86, MIPS, SPARC, ARM, something like that. What we currently don't have support for is exceptions like you could happen in signed arithmetic on MIPS, for example, or floating point instructions, because we normally don't use floating point instructions in any exploit code. And we are currently working on 64-bit support for various architectures. Okay, now that we have covered all the little bits that we need to start with the algorithms, I'm going to go over the algorithms. You can think of the algorithms that we're going to cover here like an Apollo rocket. First, you have the booster stage, which kind of like brings you into orbit, and in the case of return-oriented programming, gadget finding, it kind of like collects all the data from the binary. And in the second stage, which kind of like brings you into moon orbit or something like that, you merge all the collected data together so that you have a semantic kind of view on what is happening actually with the instruction sequences that you were looking for. And the third stage is the one where you locate the useful gadgets in the merged data. Pretty much this, you can think of it like something that you can switch, like either you can bring a man to the moon or you can like launch a satellite somewhere or something like that. So this is the part where it kind of like gets dynamically in the direction which you want to go at. Okay, what we're going to do in stage 1 algorithms. What we are doing is every native instruction gets translated into multiple RILE instructions. And from those multiple RILE instructions, we extract expression trees. And those expression trees are the one that you can see here on the left side of the screen. It's like very simple, actually. It's like if you have an addition of an integer to a register, then this is what the expression tree is going to look like. So you have operators and you have nodes that are the like registers or intermediate or integer values. That's where we're operating on. Also, what we do is we extract path information from the binary or the functions that we want to use in our return-oriented programming. So function on the right side. So how do we do this? First of all, for most of the RILE instructions, the arithmetic instructions, for example, all the handlers that we need to use to transform RILE instructions into expression trees, they are very, very simple. Because like an addition or something, because we have no side effects, takes the two registers which are input, adds them, and has this simple expression tree as the output then. But there are some instructions where we need to take special care. And one of like memory store and conditional execution are those instructions. With conditional execution, I don't know if you're all aware of this, but almost all arithmetic instructions in the ARM assembly language can be conditional. So every addition or subtraction or something can always be only executed if a certain flag is set or not. And therefore, we have the problem that as we want to only have one expression tree per RILE instruction, we need to make sure that we have some kind of way to reflect all possible outcomes of this RILE instruction in one expression tree. And that's what we're going to do here at the bottom. So if you take a look here on the right side, what you see here is basically if the condition is 0, then this side of the equation will result in the false case operation by the multiplication here, because 0 inverted is 1, the multiplication with the false operation with 1 is going to be the false operation, and down here that's going to be 0, the true operation through the multiplication is going to be 0, the addition is only going to result in the false operation. So that once we know the condition, we can execute only, or like look at only the part of the conditional execution which is actually going to happen and not all of them. So we don't have to split expression trees in this case. Also, what we need to make sure is that we have some kind of single static assignment form for all of our registers, so information doesn't get overwritten. This is true for almost all handlers, but we have a problem. Because if you have a memory store, then there is the possibility that the memory location where you write to is actually encoded into a register which you reference. But in a register-starved architecture like the x86, those registers are often used right after the memory write has taken place. So the information would get lost if we would just save the expression tree under the register name. Therefore, we need some kind of uniquely identifying our memory locations where we write to, so that this information doesn't get lost. Because otherwise, in one of the gadgets, we would write to memory locations, and later on, this memory location might be invalid, and the whole shellcode is going to crash and doesn't bring us any good. Okay, for the path extraction details, what we're doing here is we start at the free branch instruction, like the return instruction, and extract the path in reverse control flow order. That means that we start at the bottom and go to the top. Very simple there. After we have now extracted all this information, like we have all the translations for all the simple native instructions, and we have all the paths which we want to cover that are limited by a user-defined threshold or any instruction where we cannot determine the output of, like a call or a jump to some different location or something like that. We're now trying to extract the semantic information about the information that we have already extracted along the paths. So what we do now is that we take the path information and combine the expression trees that we have extracted for single native instructions along this path. Then we also need to determine jump conditions on the path, because it's totally possible that through our reverse control flow order extraction of the path that we have taken a path which is actually only taken if a certain condition is true. And if we want to use that gadget in our later compile process or while we chain gadgets by hand, we need to make sure that this condition is actually true for this specific gadget, because otherwise we cannot use it because the path wouldn't be taken. Also, the RILE translation introduces a whole lot of arithmetic garbage, kind of. So we have to simplify the result. And this is the third step in algorithms, stage 2. So how do we do that? As you can see here, we have a simple sequence of instructions. All of those instructions emit expression trees. And what we do is, for registers that are multiply named here and that might have then other information because of the instructions that sequentially follow, we can build from these expression trees here larger expression trees, and they reflect the semantic information about effects upon a specific register. So you can think of like this expression tree here is exactly what's going to happen when you execute those 4 instructions to register R0, for example. Okay. Then for the determination of jump conditions on the path, if you have one of those jump conditions here, like the branch equal to any address, but you see that your path is actually sequential, so you don't take the branch, then you know that the Z flag in the ARM case for this specific branch will not be taken. So you can generate a condition tree which actually sets the flag to this condition that you need for executing this specific path and not going down the branch. And the simplification of the result is, as you can see here, with some instruction like where you have multiple stack offsets or something like that, and there would be an addition +4, +4, +4, +4 for all the byte sequences that you add to it. You can just like simplify the result to something like that, so the SMT solver later on has a simpler game of dealing with the thing. Okay, after we have now extracted all the semantic information from the binary, we need to somehow find the gadgets that we are actually looking for, because we're not looking for some arithmetic that we can use, but we want to look for some specific things so that our Turing complete machine that we are aiming for is actually happening. What we do here is that we use a tree match handler for each operation that we are looking for and fuzzy match those trees against the expression trees that we have located in the binary. Also what we do is we use a complexity value to determine which of the gadgets has the least side effects or is the least complex one, so that we only use those gadgets which fulfill the goal of the specific operation that we are looking for with like the least side effects or like the least operations, something like that. So how do we do that? If you look at the expression trees we have here on the right side or on the left side for you, then we need to like find a specific gadget which we are looking for, like an addition or multiplication or with a specific value here in all of those trees. And we just like match this tree against all of those trees, and once we have found a match, we can use this and save the gadget which operation, where the operation fulfills our goal into the bucket of the gadgets that we were looking for. Also, you always have the possibility that two gadgets here perform the same operation, but the gadget on the left side is way more complex than the gadget on the right side, and therefore we would use the gadget on the right side because the complexity value would tell us that it's simpler to use the one on the right side than the one on the left side. So, what did I show you? First of all, that automatic algorithms for extracting gadgets from any kind of binary that you put in is totally possible. So given you have enough functions and given that they don't do all the same things, then automatic gadget search is always possible, and you will find all the gadgets that you need for any usable exploit. So even though in the original paper that introduced return-oriented programming, the Turing completeness was like one of the major issues for most of the exploits we see today. No loop is needed really, because hey, you just want to like get someplace, execute something, and then you don't care anymore. And one of the things you always have to keep in mind about gadget search is that this is very compiler dependent. Like if you look at Windows Mobile 6.1 or 6.5, you only emit code in Visual Studio for ARM version 4 or ARM version 5. But the GCC for iPhone already in the last version like emits ARM version 7 code, so it can use the way more complex single instruction multiple data instructions that the ARM set provides. So we have to have the fuzzy tree match algorithm not only find tree matches for one of those compilers, but it has to fuzzy tree match all of the possible outcomes using different ARM mnemonics in the first place, so that you can like use multiple compiler matching kind of things. And the minimizing of side effects is totally possible if the right approach is chosen. Okay, what's next? Now that we have gadgets and we know about the semantic information about that, and we know what to do exactly, we need a way to automatically combine them. And this is what Ralph's going to tell you about.
Okay, so when we first, let me advance the slide. When we first wrote the pwn-to-own payload, it was something like this, right? So, but the building blocks were much more ugly. So this game of Tetris, I don't score very high, so I have a similar score than the one that's shown here. But for pwn-to-own, we managed, but it was very tedious. So we decided it's time to automate this, and we brought in some help. So this help we call Mr. Wolf. So Mr. Wolf is our compiler. So it allows you to compile from a description of your payload together with the gadget set that has side effects, the binary payload. It's a very basic language. It's assembly-like, as was mentioned before. So don't expect a C compiler here. You could totally do something like that, but like, who needs that, right? I mean, I don't like. It's nicer to have a C compiler to write your exploits, but you don't really need that, because it's usually just short things that you do, and then you have the second stage that can be executed. So at the moment it only supports ARM, but that's because the interest is there for other platforms that's easily adaptable within, say, a weekend. And of course, Mr. Wolf always enjoys a good cyber Pompeii. So how do you live with side effects in this compiler? So we have 3 directives that allow you to tell Mr. Wolf what he can and what he cannot do in his work. So the first of these is a statement that allows you to specify ranges that can be read without triggering any faults. So these are just like maybe data or instructions in memory that you can access. Then you have memory ranges that can actually be corrupted without having any bad effects. That may be a little bit more tricky to figure out, but it's doable. And the last is a protect statement, which tells you that between two statements, or between between two or more statements, a certain list of registers should be preserved, so they should not be clobbered, because a side effect may be something like a write to memory or a read from memory, but it may also be something like a register getting overwritten. Of course, like a register being read, that's not a side effect, right? Okay, so the most important, we have several types of statements. The most important of these is the multi-assignment. So we've chosen multi-assignment because it gives the compiler freedom that we will need. So a multi-assignment is just like a normal assignment, just that you, instead of having a single value on the source and on the target side, you rather have a tuple of the same length on each side. It's useful for parallel computation as well, but we need it basically to give the compiler freedom in which order the assignment is being done. So you could express the program as a sequence of simple assignments as well, but if you express it as a rather large, as large as possible multi-assignment in each step, it allows the compiler to choose more options for you, and this gives you a higher probability of success. The second type of statement is a conditional go-to statement. So this is for simplicity. This is just a go-to if non-zero statement. So we don't do any other kind of loops. We have a call statement that allows you to interface with native library functions that are in your memory space. You have to define them first. So you have to have a list that you extract from, I don't know, the binary that you just assembled or the memory dump that you look at. To tell the compiler where certain functions are that you need. Then, of course, you need data definition sometimes. Like, I mean, you may want to read something for the hard drive that has a file name, so you need to define an ASCII string somewhere. And, of course, you have to have labels for the data and for the code if you want to reference them. Okay, so the current version of the compiler is written in Python. So actually, the payload is a Python script that pulls in this Wolf framework, and then this is why this is a very ugly hack. So this is actually the assignment operator. So yeah, you can't overload the equals operator in Python, so that's why we hacked around it that way. So this is just one line from the abstraction of the pwn2own payload into this language. So what we want to do is just we want to assign these three registers R0 to R2 before we do a call to connect. And it just assigns R0 to the value that's at the memory location sock log, assigns R1 to the pointer to this struct internet address, SYN, and the last, the R2, is being set to the size of this structure, which is defined somewhere in the program. It's just a constant, right? So now the compiler, when it compiles this multi-assignment, can do this assignment in an arbitrary order. So it can use a gadget first to assign R2, and then R0, and then R1, or any other permutation that's possible. So why do you do that? So think about having only a gadget available that whenever it assigns R2, clobbers R0. And this is the only thing that you have to write to R2. And you wrote this in a sequential manner, then you're screwed, right? This gives the compiler freedom and allows it to work in that case. Of course, this has a certain trade-off here. So, I mean, you trade this off against time that the compiler runs, because it tries different combinations. Okay, this is what loops look like. Very simple. So you just label the loop. So this clears 1024 bytes of memory, and it does a computation R2, which is not really being used, but well, I mean, who cares? Just like to show you that you can do computations. Like on the right-hand side of these multi-assignments, you can actually have arbitrary arithmetical logical expressions for computation, and on the left-hand side, those are the things that you assign to. And there's one little catch here. If anybody of you has ever done practical return-oriented programming and wanted to do a loop basically is like a conditional shift of the stack pointer. So this means that you may have overwritten things on the stack in between. So if you do that, so for instance you have called a function or something, then you need to copy that original segment back, which is something the compiler has to do. But that's like an implementation detail, but that we tripped over when we first did that. Okay, so how do we do all that? I mean, like, do we do this ourselves? No, of course not. I mean, Mr. Wolf is a very high-level problem solver, so he has some other people do the menial work for him. So actually, this menial work is somewhat brainy because you have to solve systems of equations, or actually, it's so SMT is a satisfiability modular theory problem, and in our case, we're using the theory of bit vectors and arrays. And the constraint solver that we're using actually has a third type. It has uninterpreted functions in this theory as well. It's an extension of this bit vector and array theory. And the constraint solver we were originally using was STP. We've now switched to BlueHat for a number of reasons. We had some trouble with STP. And basically what these constraint solvers do is you give them a formula or a set of formulae, and they tell you whether or not this is satisfiable or not. And if it is satisfiable, you can ask them to give you an assignment, which is sometimes called a model. Okay, so the high-level algorithm that you drive these SMT solvers with, I'm giving you an example for the multi-assignment because that's the most basic but also the most complicated. So you first find all of the gadgets that is assigned to a target. So for instance, if you want to assign to register R2 on the left-hand side in this one component, then you look for all of the gadgets that assign to a register, and you look at the left-hand side in this, sorry, at the other side as well, and you see whether it's like just a constant or whether there's a computation. And if it's just a constant, then you just look for the things that assign constants. If not, then you know that you have to connect these two sides. So in that case, it branches off into left-hand and right-hand side. Then you take the constraints that were given to you by the programmer of the payload in terms of these protect, read, and memcorrupt statements. Sorry, allow, read, and allow corrupt statements. And you take the formula that are induced by the Ryle expression trees of the gadgets, you throw them together, and you let the SMT solver do its work, and you tell you whether or not this is satisfiable. Do the same thing if it's not assigned to constant or assigned to another register for the right-hand side in each tuple. And on the right-hand side, you have the additional complexity that it can be not just an assignment to a constant or register, but it could also be an expression. So you have to build like from the innermost part of this expression, and you have to chain these expression gadgets. So that's step 4. And the last step, you connect the left-hand side and the right-hand side. Of course, you don't need to do that if all that you do in this multi-assignment is assigning constants or assigning registers to registers or memory locations. Okay, so some notes on the chaining algorithm. At first, it looks like this is an exponential complexity in the, this is like an exponential algorithm in the number of gadgets that you have. This is correct, however. It only hurts you when the percentage that actually are usable is small. So in our case, we found that it's actually it's like 95%. I haven't done exact statistics, but like I guess something like 95% are usable. So it's fast. And it doesn't matter like whether we have 50,000 gadgets or 100,000. If this were not the case, if there was just one out of these 100,000 that would help us, then of course this would really hurt us. But at the moment it's just like for each line that you compile of these multi-assignments, it's like 4 or 5 per component of the tuple that it has to try through. But that's just a heuristic. The second thing is that, I mean, this algorithm may not terminate to your satisfaction. It may tell you, oh shit, I didn't find anything that, like, I can't change this because you don't have enough gadgets, or because the gadgets are not usable like you want them to be. You made me protect too much. Or it may be that it takes just too long. Well, shit happens, then you have to think of something else and maybe rewrite your program. And the other thing I want you to realize is that the description I gave you for this high-level algorithm is actually just simply following Occam's razor. So the current strategy is not one that is maximizing the different paths that could be taken. So it's just like, it takes the simple-most route. It doesn't do something like, I'll just scribble to some memory location, and later on I will take this memory location and then connect via this memory location to both sides. You can do that, and maybe you have like, you will have higher chances of success, but at the moment we didn't run into problems with this simple strategy, so why bother? We will add that when we do. Okay, so now we switch over to the other projective, so I can give you a quick demo of the compiler. Can we just, okay, sorry.
So, yeah.
This is, okay. Oops. So here's the source. It's very simple, so you see just the first 2 lines are just pulling in what's needed. Then you define the things that the library functions that you call. You define a couple of constants. You define the memory ranges just once. You could overwrite this again. You do forward references to the data. Then you do the protect statements, and you execute the multi-assignments and the call. So this is the pwn-to-own payload abstracted into the language of Wolf. And at the end, you write out the payload. And because this takes some time, we recorded that. And this is at 15-fold speed up. So it first reads in all of the gadgets, parses them, stores them in memory, and then it compiles each of these multi-assignments. And as you see, I mean, a 15-fold speed up means that this, I think, took about 25 minutes to complete, if I'm not incorrect, or if I haven't sped up by more than a factor of 15. And yeah, now I'll hand over to Vincenzo, and he will tell you how we test the output of these things.
Yeah, so, well, I'm going to quickly say a few words because we want to show you the other demo, and then if you have questions on this, you can just ask us outside. So let's say that we are once again in the iPhone scenario. We need to test the payload. We cannot really use a jailbroken phone because code signing is disabled, and in general, like, testing there is not that close to reality as with a factory phone. So the simple plan is we get a developer phone with application that we write. We upload the application. This application reads the ROP payload from a remote server or whatever. It puts the payload inside a memory page. Make sure that this memory page gets to be the stack pointer of the application and run the payload. There are still some consideration to be done on sandboxing, but there's not enough time, so we prefer to show you the demo. So yeah. This one. Okay, so we're So we will run, can you actually read anything? Yeah. We will run a small Python web server on my computer, and we will browse to the, well, you cannot see that because I don't, yeah, just believe it.
John's fancy presentation technique.
And yeah, so now mobile Safari is going to connect to my web server. I don't know if you heard it vibrated. Oh, I forgot to run netcat. Sorry. So where is it? Okay, so here. No, can you hold this? Do 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 do. The reason for this is because the phone will connect back to to my PC and dump the SMS database I forgot. So let's do that again. Okay. Yeah. So we do have the SMS database, and you see that it's there, and we're gonna open it with SQLite, and we'll just show you an SMS. So so the SMS I'm going to show you is an SMS that Ralph sent me using his baseband station. I don't know if you, so basically, yeah, the exploit exfiltrate the SMS database from the phone, and the entire payload is a return-oriented programming payload that we are able to compile using the, well, Mr. Wolf. So now we're gonna switch back to slide deck for the last slide. We're almost done. Okay. So yeah, the further work, you can guess something, and if you have questions,
just meet us in the speakers lounge.
Yeah.